twice differentiable functions f and g, f, g, and h have second derivatives given above. Which of the functions f and g and h have a graph with exactly 2 points of inflection?
Let's underline exactly 2 points of inflection. And I'm going to refer back to the PVA card. The graph has a point of inflection when double prime changes sign. So I'm going to put on here my double prime changes sign. So I'm going to actually graph each individual. If you want to graph it one at a time, you can. If you want to do it twice or two or three, that's up to you. I think I'm going to do one at a time, so it's not overwhelming with too many graphs happening at once. So we're graphing first our f double prime. And this is almost a freebie. And when I go to my graph, I'm going to go to Zoom 6. And we're looking for how many places we're changing sign. Changing sign means above the x-axis is positive, below the x-axis is negative, correct? So we're changing sign over here. We're changing sign over here. Ooh, I think I wrote on it. So we know this one is satisfied. I'm going to put a check next to it. So we know if that one actually changed sign into locations, I can go ahead and eliminate whatever does not have F. So A can be gone and B can be gone. Now, will it be clever on your end to waste your time when G is on both of them to test that? No. Go on to H. And it looks like I might just have to modify this. Everything looks the same except it's got what at the end? -1, and let's double check. Yep, go to graph. So then we're changing sign over here. We're changing sign here, and my third one. So we know H has not 2 points of inflections, but 3 points of inflections. So we know that's gonna be gone. So it's gotta be C. And again, you don't have to test G, it's on both locations.
Aren't there 4 on the graph?
Nope.
Down, then back up, then down and back up.
It's not the direction, it's the changing sign. So positive to negative. So it's positive to negative here, positive to negative here, and positive to negative over here. That's 3 locations.
Like dips below the.
It's not how many turns. So it's everything above the x-axis is positive, below is negative. So we're looking at this guy, and this one. And that's 3 points of inflections. Okay, I'm gonna move on for the sake of the video, okay? All right, 87. Okay, on 87, Holland, go ahead and read.
The table above gives values of a function f as selected values of x. If f is twice differentiable on the interval 1 is less than or equal to x is less than or equal to 5, which of the following statements could be true?
Let's first look at the behavior. What is happening to our function? They're decreasing. So that means if I were to graph this, each part would have a slope that is decreasing. So we know f prime is negative, so we know C is gone and D is gone. And then let's kind of look at the behavior of the slope. Not the slope, the difference of the f prime. So on this one right here, we have, well, I guess we can actually find a slope. What's nice about this one, even when we're looking for the slope, because they're going up by 1, we're just dividing by 1. So what's the difference between 9 and 4?
5.
So -5, and then we have -4, -3, and -2. So are we increasing the amount or decreasing the amount?
Increase.
It is increasing, very good, B. Okay, let's go on to number 88. 88 kind of goes back to like algebra 1, if y'all remember parallel things. Okay, Alex, go ahead and read number 88.
Let f be the function defined by f of x equals ln x squared plus 1, and let g be the function defined by g of x equals x to the 5th power plus x cubed. The line tangent to the graph of f at x equals 2 is parallel to the line tangent to the graph of g at x equals a, where a is a positive constant. What is the value of a?
Let's circle the 2 things real quick. When something is parallel back in algebra 1, we know that 2 lines had what? The same. Same slope. So our slope is a derivative. So what I'm going to do is find the derivative, find that derivative, plug in the 2 into the f of x and let that equate to the other value because our slopes must be equivalent. So let's all write out f prime of x. So to recall, natural log derivative is 1 over the argument times the derivative of the argument, which is 2x. And then we're going to plug in the 2, f prime of 2. So that's going to give us 2 times 2, which is 4 on top. On the bottom, it's going to be 2 squared plus 1, which is how many? 5. Very good. And then let's derive the g of x. So that's going to give us 5x to the 4th plus 3x squared. And then it says, let's let x be a. If you want to go ahead and make it even better and waste your time and write this out, you can. But if you're like, hey, the a is already replacing x, you don't want to waste your time, that's also okay. So because the parallel slope must have the same slope, I would type this one into y1, that into y2. If you got this right, but you did not use this trick, I would practice together. Because you could remember on the AP test that we did it together, but if you physically didn't, that's going to be a sad day. So 5x to the power of 4 plus 3x to the power of 2. And our number's pretty small, so if you just go to zoom 6, it might be good. Maybe we have to zoom out. We'll see. And we're looking for where it crosses. Now, which part do I not care about? The positive or the negative? The negative, if you look at your answer choices, I don't have any negative. So second calc, 5. I'm going to go to the right. How many times do y'all remember us entering for the intersection? 3. 1, 2, and 3. And it's going to be at x equals 0.447. See it as. Now let's go on to 90. Number 90 is all about the limit definition. This right here means it's continuous, continuous, continuous. Okay, so if you want to look at your card on the limit definition, you can. But I pretty much told you. Now this one says what must be true. So I'm going to give you a visual on every one of them, except the last one, because the last one is if something is differentiable, it is continuous, right? So I don't need to prove to you on this one. So the first one says if f is defined at x equals a. All that means is there's a point, okay? So put a point. Does that guarantee that I could make a line that goes through it? Or can I choose to go outside of it? I can choose to go outside of it. Does that make it continuous? No. So we know this one is absolutely not, and it must be true. So I can eliminate B and what? B and D. Very good. So then let's worry about, looks like we have to talk about the third one. But I want to talk about the second one, though, just for the knowledge of it. So if it is continuous at the point that is defined, then the limit does exist. And then the last one, I want you to write out something. If something is differentiable, if it is differentiable, then it is continuous automatically. And the third one states differentiable first, so it's got to be continuous. So we know by the definition of continuity, C has to be the right one.